In this experiment, we will be testing the different accelerations at different points in an elevator trip. While conducting this experiment, it is important to keep in mind Newton's second law, which states the acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. So Newton's second law equation is the net force equals the mass times the acceleration.
Our initial hypothesis for this experiment is that when the elevator is either traveling up or down, but speeding up, it will have a positive acceleration, and when the elevator is traveling up or down, but slowing down, it will have a negative acceleration. Here is the weight when it is at rest, and then Avery, do you want to push the button? And now we're going up. Here we're going down.
The first step is converting pounds to kilograms. So the weight when the object was going up and speeding up was 20.4 pounds. So 1 pound equals 0.453 kilograms. So if we calculate this, that is 9.255 kilograms. So then the second weight was 19.9 pounds. And that turns out to be 9.03 kilograms. The third one was 19.8. So the mass of this one is 8.97 kilograms. Of the last one was 20.5 pounds. Which equals a mass of 9.29 kilograms. We are now converting the weight at rest to kilograms. So the weight was 20 pounds. And this calculates to 9.07 kilograms.
Okay, so the first thing we're going to calculate is the force of gravity, which stays the same throughout each different situation, and that is the mass at rest times the acceleration due to gravity, 9.8 meters per second squared, and that comes out to be 88.49 newtons. Okay, and then each time, for each different scenario, the normal force changes because the scale reads a different weight. So in the situation where it's going up and speeding up, it is the mass times the acceleration due to gravity, which comes out to be 90.65 newtons. And the second one is the weight times acceleration due to gravity, which comes out to be 88.49 newtons. And the third one, it comes out to be 87.91. And in the fourth one, it comes out to be 91.04 newtons. And this one is newtons as well.
Okay, so the equation we're using for this one is force of normal minus force of gravity equals the acceleration. So we have the force of normals all written up here, minus the constant force of gravity, which is 88.89 for all of them. So for the first one, the acceleration is 1.76 meters per second squared. So then when the elevator is going up and slowing down, the acceleration is negative 0.4 meters per second squared. And when the elevator is going down, speeding up, the acceleration equals negative 9.984 meters per second squared. And when the elevator is going down and slowing down, the acceleration is 2.152 meters per second squared.
In this experiment, there are varying accelerations because of the differences in normal forces. For instance, when the elevator was traveling upwards, it required more force between the objects and the scale, known as the normal force, to accelerate the objects upward. On the other hand, when the elevator was traveling downward, there was less of a normal force between the objects and the scale in order to accelerate them downward. So in the first situation, there's a positive acceleration because it is moving in the positive direction and speeding up. In the second situation, there is a negative acceleration because it is moving in the positive direction, but it is slowing down. In the third situation, it has a negative acceleration because it is moving in the negative direction, speeding up. And in the fourth situation, it has a positive acceleration because it is moving in the negative direction and it's slowing down.
In the middle of each elevator trip, the velocity became constant, which caused the acceleration to become zero, then causing the normal force to equal the gravitational force.